we're going to learn how to deal with objects that are on inclined planes. And we started off with a little demonstration. I'll just kind of redraw the demonstration. If we have a little toy car of science like this, or a Toyota Prius, we've got forces acting on this object. And let's say there's no friction yet. Let's draw the free body diagram of this guy. It's really simple. Now I'm going to ignore the four wheels and just say there's only one normal force. That is the ground pushing up on the car. And there's my normal force. And then this has some mass. So we've got the weight of the car, the mass times gravity. And if the car's just sitting there, then, or even if it's moving or accelerating in the horizontal direction, there's no acceleration in the vertical direction, so these two forces cancel each other out. And everything's easy. And that's kind of what we've been dealing with. But now, we're going to take our toy car of science and put it on an incline. And we're going to say this is theta right here. And theta is called the angle of incline. Or at least I'm inclined to call it that. All right, sorry. So there's our little car of science. Now we know if we let go of this thing, it's going to roll down the hill. And you've been rolling down hills on skateboards or skis or whatever, things with wheels, bicycles, for a long time. You know that if you coast downhill, you'll go faster and faster, at least until wind resistance, kind of stops your acceleration. Let's draw a free body diagram for this guy. And here's where it gets interesting. Here's my car. I'm going to kind of draw it tilted. Now, believe it or not, even if you're on an incline, gravity is still pulling you down towards the center of the earth. Gravity doesn't change, right? Gravity is, you may be on an incline now, but you'll see that, yeah, it is gravity is going to pull you down the hill, and you'll see what that is in a second. Now, we've got the normal force pushing like this. Now, here's where it's really important that you understand what the normal force is. The normal force is the force that the plane applies to the toy car in a direction that is perpendicular or normal to the plane. Well, here the plane is horizontal, so normal to the horizontal is straight up. But here, this has been inclined. So watch what I'm going to do. Here's my hand with my pencil on it, like that, and I'm going to incline it. And you see that the normal force gets tilted right along with the angle theta. As the angle of incline increases, my normal force shifts from the vertical to something that's off of vertical. Okay? Now, this is a little bit difficult to deal with. So what we're going to do for inclined plane problems, and by the way, this is like step 1, given, find, solve. Step 2, draw the free body diagram. Well, now what we're going to do, step 3, right, is to identify your x and y direction. And now we're going to shift the way we draw our x and y direction. I'm going to say, well, what do I know? I know this car is going to accelerate down the incline, right? So I'm going to make that x, and I'm going to make this y. Is that legal? Absolutely, that's legal. Who says that x and y have to be horizontal and vertical? X and y can be anything you want it to be, as long as x and y axes are perpendicular to each other. So these are still perpendicular to each other. Now, what did step 3 of the procedure tell us to do? Well, after we identify our x and y direction, we break up the forces into their x and y components. And I encourage you, when you do these problems, have your equation list out and put those 5 steps on your equation list so you can use them when you do the problems. And look, this is all in the y direction, isn't it? See, y is perpendicular. But look at gravity. Now gravity, it's still straight down towards the center of the earth, but I tilted the xy axis. So I can now break up the weight force, the force of gravity, into x and y components. You see, before, the weight was all in the y direction. But now, the weight has an x and y component to it. And so I'm going to say, well, here's the y component, but it's going down, and here's the x component of weight. Does that make sense to everybody? And I want you to look at this very carefully right now. You really got to think about this, because inclined plane problems are some of the more difficult problems we do all year long. This component, the x component of my weight, do you see that it's parallel to the incline? Like, here's the incline right here. It's parallel to the incline. This part right here, this is perpendicular to the incline. So this component is perpendicular to the incline. This component, parallel to the incline. Some people actually call this the parallel force and the perpendicular force. I wish, our book did. But that's okay. Now, let's think about our angle here. If this is our angle of incline right here, and this angle of incline, we rotate up by theta. Do you see that if we rotate up by theta, that this y component of the weight gets rotated by theta? You see, the weight was straight up and down, but now the y component of the weight gets rotated up by the angle of incline. So here's your angle of incline here, and that angle of incline is right in there. So here's my weight, still straight down towards the center of the earth. And really, the weight, the total weight of the car, is the hypotenuse of this right triangle. Here and here are the legs of that right triangle. Now this leg right here, this y component of the weight, do you see that it's the adjacent leg? It's adjacent to the angle. Remember, we said cosine theta is the adjacent over the hypotenuse. Do you remember that? And that's the definition of cosine theta. Well, what's the adjacent? Well, this is the y component of the gravity. You can see that mg in the y. And then what's the hypotenuse? Well, it's just mg, right? And so I can say that mg in the y component of the weight, this is just equal to mg cosine theta. Now this is a little bit confusing. So just think of this. If this is mg right here, the hypotenuse is mg, then this is mg cosine theta. Now here's what freaks people out. And let me zoom in on this a little bit. A lot of people get freaked out because wait a minute, whoa. This is the y component and you're using cosine theta? Yep. We are. Because this is not, right here, this is not polar coordinates. This is just the adjacent leg of a right triangle. And here's our angle of incline over here. Well, that shows up in this triangle over here, and it's just mg cosine theta. It's because we're actually measuring the angle from the vertical instead of the horizontal also. And now what about this part right here? Well, this is opposite. So this is going to be mg sine theta right here. Now I kind of crowded that up, so I'm going to redraw it. Here's my toy car on the incline. Here's my weight. I'll draw it like this. Here's my weight, because it's the hypotenuse. Here's mg cosine theta. And here's mg sine theta. These are perpendicular. This is parallel to the incline. Here's the incline. Here's mg sine theta in this direction. Mg cosine theta is perpendicular to the incline. So we have resolved or broken up the weight into x and y components. Now we can go on to step 4 of our procedure. Let us sum the forces in the x direction equals ma in the x direction, and we will sum the forces in the y direction equals ma in the y direction. Now let's look in the x direction first. Look at the free body diagram. What forces are in the x direction? That is like this. There's only one, and that is the component of the weight that's pulling it down the incline. Now, is there acceleration in the x direction? Yes, right? If I release that car, it's going to accelerate down the x direction. Yes? So that there is. That's going to be equal to ma in the x direction. Now let's look in the y direction. In the positive y direction, I look at my free body diagram, and I say in the y direction, there's the normal force, and then in the negative y direction, I've got this component of the weight. But it's in the negative x direction, or y direction, I'm sorry, minus mg cosine theta. Now what does this tell me? Well, in this case, hey, the normal force is going to be the weight times the cosine of the angle. And this makes sense. If the angle of incline is 0 degrees, well, the cosine of 0 is 1. So mg times 1 is just mg, and so the normal force is just supporting all the weight, which is what's happening up here. But if the angle is 90 degrees, the cosine of 90 degrees is 0. So if you were to hold the incline straight up, if you were going off a cliff, the normal force would be 0. Well, let's look in the y direction. Oh, mass cancels. So in both terms, on both sides. And so we can say, hey, the acceleration is just g sine theta. So in this case, the acceleration of the car is equal to 9.8 meters per second squared times the sine of the angle of incline. And there we go. And this makes sense. If the angle of incline is 0, well, what's the sine of 0 degrees? 0. 9.8 times 0 is 0. So the acceleration is 0. Right, if we're like this, it's not going to accelerate. What if I went off a cliff so my angle of incline was 90 degrees? The sine of 90 degrees is 1. And so my acceleration will be 9.8 meters per second squared. Straight down. All right. Now, we are running out of time, but I want to show you how to apply this to a problem that might involve friction. So suppose this is what you were given, and this will take 1 minute. So please don't put your stuff away yet. Here's theta. Here's a crate. Let's say we're pulling this crate up. So now we've got a pulling force, but now we've got a mu, a coefficient of friction. Let's say that the acceleration equals 0, but our velocity is a constant, and we're pulling it up the incline. How do we handle this problem? Let's say we want to find FP. Well, here, let's solve it, and let's use the procedure. Let's say I give you the mass. I'm not going to plug any numbers in here because we don't have time. mg, normal force, pulling force. Now, if I'm dragging this thing up the incline, I've got a force of friction like this, friction force. That step, and those are all the forces acting. Let's make this x and this y. So this becomes mg cosine theta, mg sine theta. Sum of the forces in the x equals ma in the x. Sum of the forces in the y equals ma in the y. I know I'm rushing through this, sorry. In the x direction, lots of forces. The pulling force minus the force of friction minus mg sine theta equals, well, it was given to have 0 acceleration. Here's an equation I can work with. Sum of the forces in the y direction. Normal force minus mg cosine theta equals 0. Finally, last thing. I know that the force of friction is equal to mu times the normal force. So you can solve for the normal force from here. Then you can solve for the force of friction and plug that in here and solve for whatever unknown you have. So that's a real fast look at, and by the way, I could have acceleration here or not or whatever. There's a lot of variations to it. Thank you for your patience. That is all.